was like a lathe or something?
So it's my pleasure to introduce Margaret Duffy. Margaret got her BS degree in math from Haverford College in 2015, and she's been at MIT working with Paul O'Gorman since then. And yeah, we've been working together on this work that she's going to talk about. And yeah, I think that's it. So looking forward to the talk.
Okay, hi everyone. Thank you so much for coming. I think I've left plenty of time for questions, so feel free to stop me and ask me any question you want. So today I'm going to be talking about the response of precipitation to climate change over tropical oceans. And in particular, I'm going to talk about a mechanism by which gradients of low-level temperature or low-level warming is influential for this precipitation response. So again, I'm Margaret Duffy, and this is work that I've done in collaboration with my advisor, Paul O'Gorman, and with Larissa Back, who you all know. So I want to motivate this by talking about how GCMs do at simulating the response of precipitation to climate change. This is a figure from an IPCC report, and it's showing the response of precipitation to climate change globally. And where there's stippling indicates some degree of agreement across the GCMs. And we can see in the tropics, which are banded off here, 20 south and 20 north, that's the region I'm going to talk about today. We can see that there's not a lot of stippling in that region, which indicates that the models aren't doing a very good job of agreeing on the precipitation response in that region. So I'm going to make this point again in a different way. Now I've picked two different GCMs. And I'm going to orient you a little bit with this figure here because I'm going to have a lot of figures that look something like this throughout the talk. So this is the tropics, 20 south to 20 north. And we have the Pacific Basin in the middle, the Indian Ocean over here, and the Atlantic over here. Blue is regions of increase in precipitation, and red is regions of decrease in precipitation. And I'm defining climate change as the difference between the end of the 20th century under RCP 8.5 conditions and the end of the 20th century under historical conditions. So here what I've done is I've picked two different models that have very, very different precipitation response patterns. Both are responding in a very big way to climate change, but they differ in their pattern. And so this makes us want to study what the GCMs are doing that's causing, what are the mechanisms that are producing these very different patterns. So I'm going to talk about three mechanisms that have come up a lot in the literature that I'm going to talk about today. One is the Whitewater Mechanism, and you've probably heard of many of these. The Whitewater Mechanism describes climate change as enhancing the historical precipitation response. Warmer get wetter describes the precipitation responses following the SST response. So where SST increases a lot, we see increases in precipitation according to this mechanism. And when it increases less, we see decreases in precipitation. And then the idea that the portion of surface convergence from SST gradients is important for precipitation has been around since Linton and Meagham 1987. And this has been talked about a lot for the control climate. It hasn't come up as much in the climate change literature. So now I'm going to just talk a little bit more about each of these three mechanisms. The Whitewater Mechanism may be familiar to some of you. It's emerged in the literature in various forms. Chu and Nealon have a similar mechanism that they came up with using a gross, a moist static energy budget. And they have a mechanism that comes out of that called the rich get richer mechanism. Hull and Soden came up with a similar mechanism using a moisture budget and found that precipitation minus evaporation response follows precipitation minus evaporation in the control climate. And so we have kind of a mechanism that's analogous with portions of these mechanisms in our work. And then the warmer get wetter mechanism was introduced by Xi et al. 2010. And the idea behind this mechanism is that precipitation increases where SST increases and where SST doesn't increase by as much. And where this comes from is the idea that the precipitation is following the gross moist stability or the gross moist instability of the atmosphere. And that gross moist stability is proportional to the moist static energy in the upper troposphere, or the difference in moist static energy between the upper troposphere and the lower troposphere. And if you remember that moist static energy includes temperature and humidity, and you also remember that the upper troposphere doesn't have a lot of water vapor and tends to have this weak temperature gradient approximation. There's not as very much of a gradient in moist static energy up here, but there is at the surface. There's SST patterns, and according to G et al., the humidity and the SST go somewhat hand in hand. So by that reasoning, the difference in moist static energy between these levels is its pattern mostly follows SST pattern, and therefore the gross moist instability and precipitation response follow the changes in this SST pattern. And then I have another oversimplified sketch, and here this is about surface convergence and the idea that the portion of surface convergence that comes from SST is important for precipitation. So here I just have flow following, from colder to warmer SSTs, and that forms convergence. That creates this convergence, and we can get, since we're in the tropics, that's convergence of moist air, and we can get this upward motion that can form clouds and precipitation. And this is an idea that's, again, been talked about a lot for the control climate and how tropical precipitation works in the control climate, and we're going to apply this idea to climate change. Okay, so I've just introduced three mechanisms. The question I want to ask is, what is the relative contribution of these three different mechanisms to the precipitation response to climate change? In particular, we're studying the response over tropical oceans. So to answer this question, we're going to use this approach. We're going to start by using a simple model of precipitation that includes a term for each of the three mechanisms I just described. We're going to apply that model. It's a two-mode model that some of you may be familiar with and that one of you invented. We're going to apply that to climate change using the CMIP5 models, and we're going to evaluate the relative contribution of each mechanism by isolating the terms in the model that correspond to that mechanism. And so I'll go through this, but this is just an overview of what we're going to do. So I'm going to start by introducing this two-mode model. Some of you are probably familiar with this. This is the paper that derived the two-mode model. It was derived for the control climate, and we're applying it to climate change here. So here's an overview of the model and why it's useful for this work. It's a two-mode model. It starts with the dry static energy budget, and then it relates monthly mean precipitation to monthly mean SST and monthly mean surface convergence. It's called the two-mode model because vertical motion is divided into its two modes of variability, and there's a shallow mode and a deep mode. And that shallow mode is related to surface convergence, and then the deep mode is related to surface convergence and SST. And the reason why this is useful for the climate change context is that when applied to climate change, it ends up having a term that corresponds to those three mechanisms that I introduced. And so we can isolate them to study the mechanisms. Okay, so I'm going to go through the two-mode model. Some of you are familiar with this, and will have to bear with me. We have made some changes to it, so that part might be a little bit new. So the steps to deriving the two-mode model are that we're going to start with the dry static energy budget, and we're going to keep the terms that dominate over tropical oceans. One of the terms that dominates is the vertical advection of dry static energy term, and that has an omega in it. And we can apply the two-mode approximation to omega such that there's a shallow mode and a deep mode. And then we can also apply the two-mode approximation to the radiation term, which is also one of the dominant terms. And then, because we've made this two-mode approximation, there are two mode amplitudes. There's a shallow mode amplitude and a deep mode amplitude, and we relate those to things that we know how to think about, in this case, surface convergence and SSD. So these are the steps I'm about to take. So, like I said, we start with the dry static energy budget, and we keep the terms that dominate. Again, I'm just following the Back and Brotherton 2009 paper here for the most part. So we have monthly mean precipitation on the left, and that's over tropical oceans, mostly balanced by vertical advection of dry static energy and by this radiation term. And the other terms tend to be smaller. And you'll notice here that I've reminded you what dry static energy is. It's proportional to temperature and geopotential height. So when we take the dominant terms, this is what we end up with over tropical oceans in a monthly mean sense. So now I'm going to focus on that vertical advection of dry static energy term. It has an omega in it, and that omega, the two-mode approximation can be applied to that omega term. And the two-mode approximation comes from an EOF analysis, which some of you are probably familiar with. It's a statistical analysis that divides the omega term into a structure function that's a function of pressure in this case, and then an amplitude that's a function of horizontal space and time. This would be an equal sign if we had an infinite number of terms here, but we keep the two most dominant terms for the two-mode approximation. When we can apply this to era interim reanalysis, omega from era interim reanalysis, and take a look at what those modes look like, and that's what's up on the screen here. The mode labeled 1 describes most of the variability, and the mode labeled 2 in the dashed line describes the second most variability. But following Back and Brotherton, we take a linear combination of those modes without losing any of the variability explained, such that one's a shallow mode and one's a deep mode. We do that by constraining the deep mode, that's the blue dashed line, to have zero surface convergence. And then we allow the shallow mode to be orthogonal to it. So those are our constraints. That's how we get our linear combination of the EOS, such that we have an approximation for omega that has a shallow mode and a deep mode. Yeah, so those modes are in blue here when they come out of era interim reanalysis. So that same two-mode approximation can be applied to the radiation term. The radiation term is influenced by clouds and water vapor, and that those interactions vary depending on where the clouds and water vapor are in the atmosphere in terms of height. And therefore, it's convenient to have a shallow portion and a deep portion. So we just use this multiple linear regression to approximate our radiation term using the shallow mode amplitude, the deep mode amplitude. And the R's are just regression coefficients, they're just constants. And like I said, the reason why this kind of makes sense is that we can have now this sort of clear sky, uniform water vapor portion here, and then this portion has to do with low cloud water vapor radiative effects, and this portion here has to do with high cloud water vapor radiative effects. Okay, so I'm going to pause here. What we've done is we've taken the dry static energy budget, we've kept the vertical advection term and the radiation term, and we've applied this two-mode approximation to both of those terms. Here's that vertical advection term, here's that radiation term, and this was the right-hand side of our equation before. And now we can see that when we've made this approximation, the vertical advection term has a coefficient in front of the shallow mode amplitude, and the radiation regression has a term in front of the shallow mode amplitude. And we combine those to get these sort of dry stratification, this dry stratification term for the shallow part of the atmosphere, and similarly for the terms that are in front of the deep mode amplitude. we can approximate these stratifications as being horizontally uniform, so uniform in space and time for a given climate. That's pretty good because the temperature tends to be fairly uniform throughout the tropics, over tropical oceans. And when we combine these, like I said, these are just the coefficients on the shallow mode amplitudes. And so when we combine them, our dry stat, the right-hand side of our dry static energy budget looks like this. So now the M has been approximated as a constant. The R naught is a constant from a regression coefficient, and the only thing that has spatial structure here are the O's. So now we have to deal with these O's, right? Like, what does that mean to be a mode amplitude? So the shallow mode amplitude is related to surface convergence using mass continuity. And then, yeah, so that's pretty straightforward. That AS is just a constant that was derived from the mass continuity equation. And this is just saying that the amplitude of vertical motion in the shallow part of the atmosphere is related to surface convergence. And then the deep mode amplitude is related to surface convergence and SST, and this is a little bit different from the original Beckett-Brotherton paper if you're familiar with it. And we just use multiple linear regression for the deep mode amplitude with relative SST and surface convergence as the predictors. So these B's are just regression coefficients, they're just constants. SST was initially included in the model to represent sort of convective instability ideas. We've changed it from SST to relative SST to better align with the warmer get wetter mechanism. And then we've included surface convergence in this regression because as a way of including the shallow mode amplitude in this regression. So what this is saying is where there's lots of vertical motion in the shallow part of the atmosphere, there's likely to be vertical motion in the deeper part of the atmosphere. And the reason why that makes sense is that the shallow convection tends to warm and moisten the atmosphere, which, because of entrainment, makes the conditions sort of preconditions the atmosphere to be favorable, to have favorable conditions for deep convection.
Margaret, does that imply there's physically a handoff between one mode and the other on a consistent, systematic basis, or is that just an approximation that makes the model work better?
What do you mean by handoff?
Well, if you have a collection of shallow mode convective clouds, do they necessarily lead to some deep convection in the same environment?
No, and so that's why we have two modes, right? If that were true, we could just do it with one mode.
That's why I'm confused about the last point. Maybe it's just, I'm sure it's naivete, but if you make the conditions favorable for deep convection, all you're doing is making them favorable. You're not pushing them over the edge.
That's right.
Okay,
yeah.
I see. Okay.
Yeah, that's right. That's what we're saying, and that's why
Okay.
that's not the only thing that's in here. We also have SST.
Okay.
I'm going to show you here how this looks. So because this is, I'm just spending a little bit more time on this because this is new and diverges from the original model. So what I've done here is I've binned the deep mode amplitude using aeronym reanalysis as a function of surface convergence on the x-axis here and relative SST on the y-axis here. For surface convergence, I'm using quick scat observations, and for the relative SST, I'm using NOAA observations. The white contour here shows, like bounds a region where the most data is. I think it's something like if there's at least 100 grid points that fit these characteristics for SST.
What do the colors indicate?
Oh yeah, sorry, I lost my color bar. Yellow is more positive OD. The black contour is the zero contour, and blue is more negative. So we can see here, what we're seeing here is that where there's lots of surface convergence and high relative SST, there's lots of deep convection, and then or more likely to have a high deep mode amplitude, and then that sort of tapers back as the surface convergence goes down and as the relative SST goes down. So this is from data, and then this is what it looks like using our regression. And we think it does pretty well. We think this is pretty good. We're happy with this. The zero contours, this thick black contours in about the same place. Yeah. Okay.
And the model just doesn't have as many lower SSTs? Why don't you capture that?
Oh, down here?
Yeah.
Yeah, we mapped out the regions, we blanked out the regions that would lead to negative precip, based on radiation, the radiation term, and the other things in our budget. And we've done that also for actually, so yeah, so let me spend a little more time on this question. We've done that for both of these, and there's more missing data for the approximation, because, and you can kind of in your head imagine what this would look like as you went down. This would get super negative super fast. So this approximation doesn't hold very well in regions with low relative SST and low service divergence. Okay, so we've done it. We derived the two-mode model. Here it is. It doesn't look as much like the dry static energy budget anymore, but this is an expression for monthly mean precipitation as a function of surface convergence and SST with the spatially varying inputs. You'll recall that we treated M as a constant stratification term. The A is a regression coefficient, so it's just a constant. The B's are regression coefficients, so they're constants. And the R naught was from the radiation regression, so again, a constant. There's one thing I haven't talked about here, which is this heaviside function. It doesn't play a very big role, but basically what it does is it prevents us from having negative precipitation. So if any of our approximations cause precipitation to be negative, it just sets it to 0. Again, that doesn't end up playing a very big role, but it's there. Okay, so how does this do? Finally, a map. Something we can look at. So this is just for the control climate. We have observed precipitation over tropical oceans in the top panel, and the two-mode model estimate of that precipitation in the bottom panel. And again, this big basin in the middle is the Pacific Ocean, the Indian Ocean's over here, the Atlantic is over here. And we can see that in the control climate, this model does pretty well at capturing the broad features of precipitation. And so we say, okay, good, let's apply it to climate change. So here are those two GCMs that I had in the introduction, the GFDL model and the MPI model. And these are chosen because their precipitation patterns are so different. And so the top row here shows the precipitation response to climate change just straight out of the GCM. And again, I'm defining climate change as the difference between the end of the 21st century under RCP 8.5 conditions and the end of the 20th century under historical conditions. So here's what that looks like if you just spit it out of the GCM. And here's what the two-mode model estimate of that precipitation looks like. So what we've done is we've calculated all those coefficients, all those many coefficients using GCM data, and then put SST and service convergence, monthly mean SST and monthly mean service convergence from the GCM into the two-mode model, and this is how it does. So we can compare the GFDL model and the MPI model separately. And to me, the takeaway from this is that even though these two GCMs have very different responses to precipitation, or precipitation responses to climate change, the two-mode model does a pretty good job in both cases. It's capturing this variability across models. So that means that mechanism that we were looking for, or those mechanisms, whatever the case may be, that we were looking for in the beginning, that I motivated in the introduction, that gets at why the precip responses are so different. It means that mechanism is in here and we can find it, which is great. Okay, so here's that two-mode model again. We've seen this already, but this time, and this is, sorry, a little bit hard to see on this projector, but I put in gray the terms that don't have a very big contribution to the precipitation response. We looked at them, and it didn't make that big of a difference. And conveniently, the only terms that are left are the terms in black, which conveniently, conveniently align with the proposed mechanisms that I introduced in the introduction. So that's good. That's reassuring for the science so far. And so, to evaluate the contribution of that term of that mechanism, we just isolate it. We just say, okay, how much we can just say how much does each one contribute to the total precipitation response, leaving everything else fixed. So the wet get wetter mechanism can be evaluated by isolating the changes in the stratification terms. The surface convergence mechanism can be evaluated by isolating changes in surface convergence, and the warmer get wetter mechanism can be evaluated by isolating changes in relative SST. So here's the GFDL model. On the left here, this is what we've seen already. This is just the precipitation response that the GCM spit out. And this is the two-mode model estimate of that response. We've seen this already. And now we can divide that response into the contribution from each of the three mechanisms. So the wet get wetter contribution is shown here. Again, blue is regions of increasing precipitation, and so we can see that the wet get wetter mechanism is contributing positive anomalies. And these anomalies are where there tends to be lots of precipitation in the control climate. The warmer get wetter mechanism is here, and it's weak, surprisingly weak, except for this negative anomaly in the South Pacific. But it's not negligible, but it's pretty small. It's surprisingly small. And then the surface convergence contribution is quite substantial. It's contributing both positive and negative anomalies. It has lots of spatial structure.
When you use the surface convergence, is that the full longitudinal extent, including over land, or is it just over the basins?
Just over the basin.
Why isn't the convergence and divergence over the land a part of it? Physically?
Yeah, I mean, we're just looking locally.
Okay. So it's a regression literally at each point?
Yeah.
Okay.
Yep.
Okay.
Good point. But I'm going to talk more about the surface convergence term in a second. Okay, so these are our mechanisms for one model, but remember we had another one with a totally different precipitation response. So how does that do? So here's that totally different precipitation response and the two-mode model estimate of the totally different precipitation response. And the wet get wetter contribution is, again, contributing positive anomalies where there's lots of climatological precipitation. Warmer get wetter is, again, actually it's even smaller in this case, so not negligible, but just not as big as we would have thought given how important it is in the literature. And this surface convergence contribution looks pretty different from the one on the previous slide, but it continues to contribute both positive and negative anomalies and just generally be very important for the precipitation response. Okay, so I put in gray, in this gray box here, what our original question was, what the original intent was. So now what was the relative contribution of the three mechanisms to the tropical precipitation response to climate change over oceans? And we found basically that even though the patterns of the precip responses are so different across GCMs, the importance of each mechanism, just in a general sense, is pretty robust. And while all three mechanisms are important, the surface convergence contribution is really strong, and the warmer get wetter mechanism is surprisingly weak. And the surprisingly comes from what we've seen in the literature. It's just warmer get wetter has received a lot of attention in the climate change, in the precip climate change literature, and surface convergence hasn't as much. So that's why I say surprisingly. This would be a good time for questions. Yeah.
So did you say that surface convergence was more important for the top-heavy profiles? Is that right, or it's more important for one of the two profiles, or?
So I wouldn't say it's more important. It contributes to both, and so the shallower profile is set exclusively by surface convergence in this model, and then the deep one is set partially by surface convergence and partially by SST. But then in general, the deep mode is contributing more to the precipitation response. So I couldn't really say, it's kind of a balance of two competing effects. So I couldn't really say whether surface convergence is more in one or more in the other, but it's important in both.
Can this methodology be used to address this idea of Linson? You have a relative link, and can you probe the parameter space to see, are there ways that tropical convection can cool the planet?
Can what?
Cool the planet off under a warming scenario, be a negative feedback. I mean, it seems like maybe
Yeah.
your methodology could be used for
Yeah.
something like that.
Yeah, we haven't tried it, but in theory, yeah. Okay, so the surface convergence response to climate change is so important for the precipitation response. So we study it more. We're going to just spend more time on this surface convergence response. And in particular, we want to know how well it's related to SST gradients, right? I mean, that's been the idea in the control climate. And so we look at that more. So just to kind of prime you for this section, here's the response of surface convergence to climate change. This is the ensemble mean across a bunch of CMIP5 models. And so we have this negative anomaly in the northern part of the tropical Pacific, this positive anomaly in the equatorial Pacific, the negative anomaly here, some smaller anomalies in the Indian Ocean and the Atlantic Ocean. That's what it looks like. And then if you were to go strictly based on the Linson and Negum ideas, you would get some portion of surface convergence as being proportional to the Laplacian of SST. So we just plot the response of the Laplacian of SST here, and we compare it to the relative SST, which is the term in the warmer get wetter mechanism. And these are correlations with the surface convergence response here. And so we can see that the surface convergence response, I mean, all three of these have some similarities with one another, but the surface convergence response seems to be a little bit more aligned with the Laplacian of SST. And so as you can probably guess, I'm about to derive an expression for surface convergence that's proportional to the Laplacian of SST. So this is to motivate you as to why that might be a good idea. But before I do that, I just want to talk about the Laplacian of SST. We don't hear the word Laplacian every day necessarily, unless you're me. And so I just want to talk about the features and what that means. Maybe other people hear the Laplacian used every day, but I just want to talk about it a little bit more since it's important. So here's just an idealized SST anomaly. This is the expression for it. It's got a sinusoidal pattern in X and then decays exponentially in Y. I have a warmer SST over here and a cooler SST anomaly over here. This isn't a pattern that we're using in this work necessarily. It's just an idealized pattern. This is what it looks like for relative SST, right? That's what was important for that warmer get wetter mechanism. And so we just subtract off the mean pretty much to get the change in relative SST. And so this is what it looks like. And then if we take the Laplacian of SST, this is what it looks like. This is actually the negative, because that's what we end up using. So there's a couple of features I want to point out here. First of all, the Laplacian of SST, it doesn't care about the mean warming, right? This background, this C could be anything. It could be, I could be imposing this pattern on a 290 Kelvin ocean or a 300 Kelvin ocean. The Laplacian stays the same. So the Laplacian for relative SST and the Laplacian of the total SST response are the same. It doesn't care about the mean. The Laplacian also only cares about local gradients. It doesn't care about what's going on far away. So if you were to put a huge anomaly over here, a big enough anomaly that it changed the mean SST, the relative SST over here would change, but the Laplacian of SST would not change over here. It would only change where you put in the anomaly. So it's a more local metric in that sense. And another point to make is that the extrema of the Laplacian of SST and the SST itself tend to be co-located. They are in this example. And so, yeah, you can just see that the peak, the maximum in this negative of Laplacian of SST is in the same place as is the SST anomaly itself. And same with the minimum. Okay, so now I'm going to go ahead and keep going with that derivation of an expression for surface convergence that's proportional to the Laplacian of SST. And that derivation starts with the mixed layer model from a different Brack and Brotherton 2009 paper. Here it is. Some of you may be familiar with it. And that mixed layer model incorporates ideas that Lindzen and Needham put forward in 1987, just kind of in a little bit more modern way. And so we use that as a starting point for the derivation for our expression. So here we are. This is 4 steps this time instead of 5. We're going to come up with an expression for surface convergence proportional to the Laplacian of SST. So we start with that mixed layer model that I mentioned, and we keep the terms that dominate over tropical oceans. And one of those terms, or well, 2 of those terms are the surface pressure gradient terms. We can relate the surface pressure gradient to boundary layer virtual temperature using the hydrostatic approximation combined with the ideal gas law. When we do that, we end up with a term for in the surface convergence expression that's proportional to the Laplacian of boundary layer virtual temperature. And we hang on to that approximation. I'll show results from that approximation later on. And we also take it another step further and relate the Laplacian of boundary layer virtual temperature to the Laplacian of SST to get this expression for surface convergence proportional to the Laplacian of SST. So here are the steps we're going to take. Here's the first one. So this is the statement of the mixed layer model here. It's based on momentum conservation. The U and the V are, since it's a mixed layer, so it's the bulk boundary layer winds in that mixed layer. And then the original model had all sorts of terms, including, in addition to the pressure gradient terms, including the Coriolis term and effects of momentum mixing from above the top of the boundary layer and surface drag. The Back and Brotherton paper showed that some of these terms are small, and what we're left with is an expression for U and V that's proportional to gradient and surface pressure. So here's what that looks like when we just keep those dominant terms. So I'm going to focus on these horizontal gradients of surface pressure, which appear in both the U and V terms. Yeah.
It seems when you're doing it that way, you're losing the effect of exponential moisture. The impact of the I forget the
Clausius-Clapeyron?
Clausius-Clapeyron, yeah, the Clausius-Clapeyron equation. By going del squared T is related to del squared. You're saying del squared TV is related to del squared SST, but what about the virtual temperature part? Because that will go a little differently, it seems.
That's true. Yeah, you're right. Yeah, we're losing that a little bit. Yeah, and we checked that out, right? We compared T versus TV, and using virtual temperature instead of temperature does have a little bit of improvement. The G et al. Paper had this argument that humidity and temperature kind of go hand in hand a little bit to first order. So that may be why we're not totally falling apart when we do this.
It seems like it would be easy to do, to modify it to have the Clausius-Clapeyron.
I mean, we could just use virtual temperature of the surface for one thing. Yeah, that's true. Yeah. Yeah, that's right. Okay, so we're focusing on those pressure gradient terms. And so what we do is we relate surface pressure to boundary layer virtual temperature using the hydrostatic approximation and the ideal gas law. This is probably familiar to many of you. We've just integrated through the boundary layer, which we, in practice, just integrate up to 850. We take gradients of this term, and when we take the gradients, we just keep the term is proportional to gradients in temperature. And so when we do that, this is what we get. We get this expression for pressure gradients that are proportional to temperature gradients integrated through the boundary layer. So we can plug that expression, those approximations for pressure gradients, back into the mixed layer model. And one of the terms, when we take the convergence of that, because we had a derivative for the pressure/temperature gradient, and then it's U and V, so we take surface convergence, that's another derivative, we end up with a term proportional to the Laplacian of boundary layer virtual temperature. And this is that term, this is what that term looks like, and we keep this and call this our first surface convergence approximation, the one that's proportional to the Laplacian of boundary layer virtual temperature. And then we take this one step further and relate the Laplacian of boundary layer virtual temperature to the Laplacian of SST. There was if you recall from the previous slide, there was a TV squared in the denominator. We swapped that out for SST squared, and then for this Laplacian of TV squared in the numerator, we relate it to the Laplacian of SST. And what we do is we say, okay, there's an SST gradient at the surface, but then by weak temperature gradient approximation, there's not so much of a temperature gradient higher up. And so we just, and Lindzen and Nygam have ideas about this, or have a piece that justify doing this. They have sort of similar, but slightly different approximation. So what we do is we just say, okay, that SST pattern is decaying with height. And we assume that it decays by half by the time you get to 850 hectopascals, and this is the expression that represents that concept. And so that is how we relate the Laplacian boundary layer virtual temperature to the Laplacian SST. And of course, we are now neglecting the virtual part of virtual temperature. And so here are two surface convergence approximations, or two versions of the same surface convergence approximations. The top, again, is just an expression for surface convergence proportional to the Laplacian boundary layer virtual temperature, and then we have an expression for surface convergence proportional to the Laplacian of SST. And so we apply these to climate change, and let's see how we do. So we've seen this already, this is the response of surface convergence to climate change, just straight out of the GCMs, an ensemble mean. Here's how the mixed layer model does, the full mixed layer model, nothing neglected, does at estimating that surface convergence response. And then in panel C, I have our boundary layer virtual temperature surface convergence approximation and our Laplacian of SST surface convergence approximation. We can see that as we make approximations, we introduce errors, but the general pattern of this, especially in the Pacific, of this negative, positive, negative anomaly is carried through even as we make pretty substantial approximations. And this sort of positive anomaly in the sort of disappears and shows back up. So it's not perfect. I mean, it's a little bit crude. It's not perfect. But it does okay at capturing the features in a broad sense. Okay, so we've done two things here at this point, right? We've decomposed the precipitation response to climate change into its three mechanisms and found surface convergence to be very important, especially for the discrepancies across GCMs. And then we've related surface convergence to what we'll say gradients of low-level temperatures using these two different surface convergence approximations. So you can probably guess what I'm going to do now, which is put these together. And what we can do is we can take that original two-mode precipitation model that we looked at before, which had surface convergence that appeared in both the shallow mode and in the deep mode, and we can swap out that surface convergence that we had initially been using GCM surface convergence for with our approximations that we've made. So now we can take a look at how that looks. So on the top here is the response of precipitation to climate change, just straight out of the GCMs. This is now an ensemble mean, so it doesn't look quite like either the GFDL or MPI models that we saw earlier, because it's the ensemble mean now. And this is how the two-mode model does at estimating that precipitation response pretty well. And then, like I said, if we just swap out the surface convergence pulled straight out of the GCM and replace it with our boundary layer virtual temperature surface convergence approximation, it looks like this. And we can do the same with our Laplacian of SST surface convergence approximation, and it looks like this. And then I want to make a note here, especially for this one in panel D, that this is now an estimate of precipitation response to climate change using a precipitation model with only SST as the spatially varying input. And that SST appears both through relative SST and through its Laplacian. So I'm almost done. I have just a few more slides. But basically, these coupled models are complicated, right? So we just simplify this a little bit more by looking at them in atmosphere-only models, or in atmospheric models, the AMIP simulations. And what we can do when we use AMIP simulations, for example, AMIP has a uniform warming simulation, right? So the AMIP simulations are forced with SST. And so what we can do is we can look at the effects from mean warming and the effects from pattern of warming on the SST. And so what we do is the AMIP 4K simulation is one that exists. Some of you have probably used it. And then we can take a composite of the AMIP 4K simulation response and the AMIP future response and create a simulation where the atmosphere is responding only to the pattern of change of SST. So now we have, so what I'm going to do going forward is I'm going to use two AMIP simulations. One that's responding only to the mean warming with no pattern, and one that's responding only to the pattern of SST with no mean. Just decomposing the effects of the mean warming and the pattern of warming. So here is just the pattern of warming. There's no mean warming in this simulation. We've just changed the SST pattern in a way that's consistent with how SST pattern changes in response to climate change. And here's the precipitation response to the pattern of SST. Now this is per Kelvin. And this is how the two-mode model does it, estimating that precipitation response, which is, again, very good. The wet-get-wetter, now because there's no mean warming, the wet-get-wetter contribution is basically zero, very close to zero. There's a warmer get-wetter contribution and a surface convergence contribution. Both of these act through the mode amplitudes, and so they're both, in that sense, dynamic, contributing to dynamic, via dynamic mechanisms. And then here's the uniform warming simulation. This has a totally different pattern of precipitation response, right? And in fact, it's really only positive anomalies. And actually, it's kind of interesting, just, right, I mean, I'm just going to scroll back to the previous one. I just think these are pretty interesting because they're both really big changes, like the precip is responding both the mean and the pattern change, and just in very different ways. And we can explain that using the two-mode model because now it's the wet-get-wetter contribution that's mostly contributing to this precip response. And the warmer get wetter contribution has to be zero because it's uniform. The one we use uniform, there's no change in the relative SST. And then the surface convergence contribution is very small. And that is validating, right? Because if we approximate surface convergence using the Laplacian of SST, this would be zero if this were just the Laplacian of SST, right? Because uniform warming, the Laplacian of SST isn't changing. So it's very validating that this is small in this case. So this is just to say that these sort of simpler simulations are consistent with our findings, are consistent with what we found so far. So we have precipitation response to climate change, the mean warming, the wet get wetter is acting mostly through mean warming, and then warmer get wetter and surface convergence. The dynamic part is responding mostly through patterns of changes. Okay, here's my conclusion slide. So we've covered a lot here, but what we've learned, I think, is that all three of the mechanisms that I introduced in the beginning do matter for the response of precipitation over tropical oceans, but we're surprised by how big that surface convergence contribution is, especially as compared to the warmer get wetter contribution. And again, that surprise is just because of the prevalence in the literature. And then the surface convergence contribution, we spent a little bit more time on, and we related it to the Laplacian of low-level temperature gradients using those two surface convergence approximations. And basically, if you put those things together, what you notice or what you realize is that the SST is affecting precipitation, but not just via the warmer get wetter mechanism, also via its effects on surface convergence. And so this is a paper that myself, Paul, O'Gorman, and Larissa and I have all co-authored and submitted to Journal of Climate. We just recently submitted the reviews for it, so you can be on lookout for that. And again, I'm Margaret Duffy, and my email address is on the slide.
Very nice analysis, Margaret. What's the physical distinction between the warmer get wetter and the Laplacian of the SST grade? I can't really see what the big difference is. I certainly can't. What was the first one called again?
Wet get
The
wetter?
first mechanism? Yeah, wet get wetter. I don't understand why that would. If you pick that apart the way you picked this one apart, I think you'd find that it doesn't have much physical, sense to it. I don't know. Maybe I'm wrong about that. But I like that. I think there might be a fine distinction between the warmer get wetter and what you're talking about with the Laplacian of the sea surface temperature. Is that right? I'm a naive spectator in this field, so I'm trying to understand this.
Yeah, so let me just talk about this a little bit more, right? Because I mean, we got reviewer comments along these lines, so this is you're not the only one who's a little bit just trying to understand this role of SST and what's different about it. So I'm just and I think this wasn't quite your question, but I'm just going to put up that Laplacian of SST slide again that I had with that idealized.
Yeah, well, as you're doing that, I want to say that I completely agree that Laplacian is a major factor here, and I understand this slide very well.
Okay.
What I don't get is why would somebody think that warmer gets wetter without saying where it gets warmer? The Laplacian tells you that it's important where it gets warmer relative to everywhere else. So that's what I'm trying to understand. Why would that? Why wouldn't you jump immediately to this as the answer?
Okay, so why? Yeah. So a lot of the previous literature about warmer get wetter, some of it just did sort of correlations of SST response with precipitation response. The Gidal paper that introduced it they didn't just do that, but they did that, and then they had this scaling based on the gross moist instability. They had this explanation. Using the gross moist instability, that's what I explained here.
Yeah.
And what we're really, I mean, there's a correlation between SST and Laplacian SST, and so what we're really doing is we're kind of undermining, in a way, this explanation. We're not saying it doesn't matter at all, but we're saying really, this isn't as important as the dynamic.
Yeah, there's a boundary even in that picture. Even in that schematic, there's a boundary between more warming and less warming, which means you'll have a gradient. A divergence of the gradient vector. And so you have to have a Laplacian that's non-zero. And so that sets you up to there's a mandate that the geometry of the warming matters, is what it seems like to me.
Well, that's what we're finding.
Yeah.
But I think you're bringing up some good points, right? Which is that it's really like, and in a way, like what we're doing is we're making this a harder problem, right? Because we're saying, okay, if we want to get precipitation right, we have to get SST right, but oh no, we can't just get SST right, we have to get its Laplacian right, which is much harder, right?
Yeah.
I mean, that depends a lot on what's going on locally and the gradients. You can't have an SST pattern that, you just squint your eyes, yeah, those look basically good enough. It has to be better than that.
Right.
So kind of one of the implications is that we're making this a harder problem. I'm not sure if I've really answered your question.
It's been a good conversation. I'm not sure I articulated my question well, but I like what you said, so, yeah.
Right,
I don't think you're making the problem harder. I think you're exposing the fact that it's not simple. I think there's a difference.
Yeah, right, yeah, I'm not making it harder,
Yeah.
but it's bad news, maybe.
Yeah.
If we had a different finding, it might be a little bit easier for climate science and climate modelers to get precipitation response right. Yeah.
So in the beginning, you talked about the surface convergence as being controlled by both the precipitation pattern and the SSE, the large-scale dynamics. And in the end, you showed, at least with your AMIP simulation, that it was all, for the most part, driven by the large-scale dynamics. Is that the right way to interpret it? The fact that you got a very small...
You're saying it was in the shallow mode and the deep mode?
No, so your last figure where you said this is rewarding that the surface convergence response, the surface convergence contribution was small in this experiment where you knew that it was that it should be small. Does that say something about in the real atmosphere, about that balance between the large-scale dynamics driving the convection versus the convection kind of driving itself?
Yes, this is an interesting debate. So I think you're bringing up a good point here. Yeah, which is that, okay, we're studying the link from SST to precipitation.
Right, as opposed to the two being,
For precipitation and the atmosphere in general, just feedback,
Right.
right, on the SST. And that's absolutely right. We're studying one direction of a two-directional problem. Basically, Larissa's previous work, and I think this work maybe too, right? Because there's this convergence causing convection versus convection causing convergence argument,
Right.
and I think, well, yeah, I think, like I said, I think it's a two-issue, but this is suggesting we have reason to believe that the convergence to convection direction is a little bit stronger
On these monthly and longer timescales.
Oh, yeah. So this is a monthly
Okay.
mean SST. Yeah. Yeah.
how much does precipitation change the Laplacian of SST? Just by changing the surface volume?
Well, if anything, it works in the opposite direction.
Yeah, it cool it, right? It
It
get
would
rid of,
cool the warm
it get rid of
SSTs.
the warm SST.
Right.
Okay.
Right. But I mean, but you're right. There's this little bit of source convergence response. I mean, there is a little bit that we're not capturing. And this is, this represents something that our model just isn't getting. But yeah, I mean, yeah, the idea that basically, like, I think the atmosphere tends to, so you and I were talking about this, the atmosphere tends to, I think, smooth out the gradients, and so that suggests that actually this effect from the Laplacian of SST is like the Laplacian is mostly coming from the ocean if the atmosphere is kind of damping it out.
Makes the argument stronger.
Oh, yeah. Yeah.